Okay, well, thank you very much for inviting me and organizing this very interesting workshop. Today I'm going to talk about what some example of what could happen when the earthquake approaches the surface. This is work with contributions from a large group of people, mostly I would like to stress that these three did all the hard field work in the dust and the wind of the desert to collect data, and then experimental work too, but other people too who have been working with before contributed to some of the things that I'm going to show today. So the question is how frequent and how large are shallow slip on earthquakes faults, especially in large earthquakes, and can they reach the surface easily? So surprisingly, it's not very easy to answer that question because many of the larger earthquakes are underwater, so it's not easy to access them. They're far from geodetic and seismic instruments because you have very few on the ocean bottoms. And also it's difficult to separate what happens during the earthquake from what happens after the earthquake, not seismically or in the interseismic phase. But we know, especially with certainty since Tohoku 2011, that they can reach the surface. So I just put together the last 10, 15 years, the biggest earthquakes, and most of them, of course, are in the contours of the Pacific. And just a few of them where we know really what happened when they get close to the surface. But we know that, for example, well, we can see here the Sumatra cluster in a very few years, very big earthquakes, and over there another cluster happening, which is the South American Chilean coast. And some of the earthquakes that are shown here were described this morning talks. And then I added a couple of stars here. We represent tsunami earthquakes, which reach only specifically the shallow part of the fault. So you have shallow part of the fault that breaks in connection to a fault which generates deep-rooted earthquakes. But another example here for the Java is a tsunami earthquake that breaks a fault that is only seismic superficially, and the deep root of the fault is not seismic. And sometimes you have both the deep and the shallow part of the fault that break together. That's the case of Tohoku earthquakes. So as they say in France, tous les coups sont permis. Okay. So this is a list of a few of them. I'm not sure about this one, whether it reached the surface. Definitely not this one, and there was afterslip because some island close to the trench allowed to measure carefully what happened. Mentawai tsunami earthquake was shallow, and so on. And probably this was a sort of watershed for the way we see earthquakes at the surface, because it's definitely certain that so there was a paradigm before Tohoku that the superficial part is very difficult or almost never breaks. And now there were an inverse paradigm that seems to say that it's very easy to break through the surface because the high clay content and loose material that is in the superficial part of the fault is at high velocity is very easy to break through. So the aims of this, of course, is to see how, to try to understand how shallow faulting is behaving, and it's poorly understood so far, and also, as I think Jean-Paul said in historical earthquakes, like to surprise us. So how can we constrain better the models to sort of anticipate what's going to happen in big earthquakes? And so here I'm going to explore laboratory experiments on fault rock behaviors, theory on the rupture energy budget, and some peculiar features of faults that we observed in the shallow reaches of the faults. And so I need to be aware of the timing here. And how it could give us information that could feed back into the models. And hopefully have some practical implications for people living on earthquake-prone zones and who fight tsunami and earthquakes, as represented in a leaflet by our Japanese friends for tourists who go to Koshi. Now, the context is when fault reaches the surface, there's a very strong interaction with the free surface that creates reverberation and then amplifies the motion. The material is more compliant, is poorly consolidated very often. The normal stress is very low, so there can't be much energy stored close to the surface. And so generally it has been considered as a passive participant to the seismic slip, the superficial part of the fault. Yet the contribution to seismic hazard is very important. And then the fact that tsunami earthquakes are not deep-rooted indicates that there must be some kind of stress accumulation even close to the surface. Then there are several types in big megathrust faults of margins. Of course, some have more sediments, some have less. Those that have more sediments are called generally accretioner margins, and they have a lot of large volumes of poorly consolidated and progressively compacted sediments. They're rich in fluids, and the composition often contains a lot of clay, okay, on top of course, silicate and carbonate fossil content. The seismic velocity are relatively low. Of course, they increase rapidly with depth, up to about 7 kilometers or 10 kilometer depth. And then the faulting structure is very complex. Is that of a sort of array of faults that branch away from the main subduction channel or décollement, where most of the slip is accumulated. There are many strands which are in sequence and out of sequence, and there are splay faults in the back, which are believed to participate to the seismic motions, which are not on the main décollement. So it's a multi-scale branching which is under constant evolution, because the prism is unstable and the faulting is constantly recreated. So possibly those branches of the fault are growing episodically during also the earthquakes on very immature fault strands. So open questions and prejudice and paradox, let's say, is it unlocked, stable sliding, and therefore incapable of building stress? Sometimes the shallow part of the fault is depicted as precluding high velocity slip because it's velocity hardening, which means the faster you slide, the more friction it generates, and so it slows down the rupture. And many large, so this I've already said. There are evidence, of course, growing evidence that points in the opposite behavior, that tsunamis can earthquake only the shallow depth, and they show large shallow seismic slip. Properties of the rupture are that there's a relatively low rupture velocity, of course, related to the material. Very low radiated energy versus moment. And also, when it's not a tsunami earthquake but a great earthquake, the superficial part of the fault appears to radiate less energy. The sliding friction, if you take rocks from IODP perforation campaigns, show very low friction and very low fracture energy. I'm going to remove this little hand here. So the factors that affect the fact that rupture can continue to propagate, stop in the shallow part are things like the fact that they are rooted on a seismic part of the fault, so you have a big rupture that comes from depth, and even if the superficial part is low stress, it's going to be pushed by the incoming rupture or the co-seismic impulse that comes from deeper. Wave velocity and density adjacent to the fault are low, and so Ley and Bilek, for example, interpreted the fact that this rupture propagated slowly because the shear stiffness was low. But this is just one part of the picture. Now, inhomogeneity plays a role, and the last three arguments are those that I'm going to develop more today. Is what are the geometry, the boundary conditions, the fault structures, and especially the dissipative factors. So now just an apology here, because some models are very simple. All models are wrong, some models are useful. That's a statistician that say that. I tend to favor very simple models, even if they're more wrong, because I think sometimes they're more useful to understand what's going on. So what are the control parameters, the essential control parameters on the rupture that we want to measure from rocks to try to input in our models? And so what are we going to do in our experiments? So if we do a very simple model, we'll know what are the control parameters. So now just a few equations. I thought I may show them early in the talk, because if I showed them in the end, you would all fall asleep. Sensitive people can close their eyes. But basically, there's one-dimensionalist parameter that controls the fact that rupture will propagate, accelerate, or stop. And you can find it in different ways from different points of view by doing different energy budgets. You always end up in the same combination. So you have the length of the active rupture, which I call L, the stress drop, the dynamic stress drop, which happens in the active part of the fault, which is here in red, and the stiffness, elastic stiffness. And then you have this thing here, which is the energy dissipation by the rupture propagating process close to the tip of the propagating rupture. And so these are essentially 4 parameters, and combined together, they give you something that between 0 and 1, and that tells you how likely the rupture is going to propagate, arrest, or even nucleate. So you can get this from a classic energy budget, a la Rivera Kanamori. Maybe it's Kanamori and Rivera, but today Rivera is the chairman, so I put it first. So the radiated energy made available by the earthquake propagation, by rupture propagation, is the total energy released by the strain surrounding the fault minus the frictional dissipation minus this fracture energy. And you can write this like this. So you start to have this stress drop that appears and the slip on the fault. But the slip on the fault is related to the fault length through classic scaling relationship of earthquakes. At least after Jean-Paul's talk, I'm not so sure, but if we use classic scaling, that's the way it goes. So you can build it inside this formula and you get this parameter combination again, especially if you put this to 0, which is just barely the limit that the rupture is going to propagate, and you get this combination. Then you can do another thing, is look at the classics, and of course Griffith's work from the 30s now. You again have this parameter here, and it's being used by Andrews to explain the nucleation length of the earthquake. So, but most interestingly, if you look at a rupture that's propagating at a given velocity, at seismic velocity, you can write down the stress intensity factors, and these are the same parameters again, stress drop, length of the fault, and you can compute the strain energy flow as the square of this thing divided by the stiffness. And then you multiply that by the Lorentz construction, which is essentially the rupture velocity square divided by the Rayleigh velocity square, okay, -1, and you take the square root, and you get this expression, and that's the energy that's available for propagation, and the GC on the other side is the energy that's dissipated by rupture. And you want to compare the two to know if your rupture is propagating, and you get your rupture velocity out of that. So it's a very simple model again, to try to understand what are the dominant parameters, and you get this combination of dimensionless combination of parameters once more here. So this is all very, very well known. So this works also for a propagating rupture. The good news is we can use an inhomogeneous model because the stress drop can vary along the fault. Then you replace this by an integral. And if you make, for example, one part of the fault loaded, and excuse me, so you load this part of the fault, and you assume that it's now entering a region where the stress is very low. So you have an inhomogeneous model with 2 parts, bottom and top of the fault, allegedly. Then you have now this equation, and again you have something which is the static stress intensity, but then you have these ratio of lengths there, and you put that in your equation, and you get your rupture energy for an inhomogeneous model. And what you get if you compute the energy here against a constant dissipation of energy at the crack tip, when the rupture arrives in the region which is unloaded, it continues to propagate. It doesn't need stress because it's pushed by the energy that comes from the rest of the fault. But it gradually slows down. But if the region is small enough and it's closer to the surface, then it doesn't slow down enough before it reaches the surface, so it does continue up to the surface. And the smaller it is, the more probable it is to propagate to the surface. Now, okay, there are much more complicated models than this, of course. Curzon and Dunham modeled the full fault geometry and the wave propagation, and this is work by Murphy and other authors. And you can put inhomogeneous properties of the medium, the geometry, the surface, and change the friction law here and propagate waves. But you still get more or less the same thing. You see, if the shallow part is small, which are red, black, and blue case, then the rupture will reach the surface. If you make it too big, all the energy will be dissipated before it reaches the surface. This is another model showing similar things by Murphy. So if the rupture is relatively deeper, it will slow down before it reaches the surface. You use this equation. So again, this is the parameter that we want to measure in the laboratory. Of course, some things we can measure, others we can't. We can measure fracture energy. Yes, but what is fracture energy in real earthquakes? That's another scale. We can measure the dynamic stress drop. In theory, we get the sliding friction, which is generally very low at high velocities, but the pre-stress is rather arbitrary. Current length, of course, we don't have a characteristic length in the lab, not for rotary shear experiments, which are the same kind here as those that Giulio showed earlier on, and of course the shear stiffness. And so we have a partial view from the lab. How can we compare it to field observation? So this is typically what we saw in the lab. We see in the lab when you start accelerating the slip, you get a high peak of friction, and then it gradually slows. Usually, the faster you go, the weaker it gets. And this weakening here consumes some energy, which is there below the triangle. If you put water and clay in your samples, which is something you'd expect in big subduction zones close to the surface, this peak in friction is killed almost completely, and the fracture energy becomes very, very low. So high velocity is strongly velocity weakening, but if you do some experiments very slowly, you see that it's velocity hardening, which is just the contrary. So there's a slow behavior and a fast behavior, and they're just the opposite. This is another more recent example, which is also for some silty clays, and these are different experimental curves. And so some materials show that they have potential to generate more energy for rupture or less dissipation for rupture to propagate. And we can try to see whether they correspond to some parts of the thrusts or others. Okay, let's skip this part. So laboratory experiments, however, simulate slip on a principal fault zone which is highly localized. Usually what we get in the lab is 1 millimeter or 100 microns even, very, very thin zones of highly localized slip. But we know there's a lot of off-fault damage and a very broad fault zone in nature. Okay? How this broad damage is expressed when you get to shallow faulting, and how can it affect the dissipation? Well, we have several types of observations from perforations again, general features that we see in the field from shallow fault segments, and again, distributed network of faulting, and how is it important in the energy balance. This is another example for a paper that came out 2 days ago, and this is on the Costa Rica coast, close to the Costa Rica coast, and you have this series of branching structures that leave off the main fault here, and they seem to be partly supported by the organic oozes, which are essentially carbonatic rock, as described by Giulio earlier, and some perforation were done on these rocks, trying to understand what was the potential for seismic rupture on these branches. And this is another evidence from perforation. I believe this one was from the Nankai Trough. And you get, of course, your décollement, which is your main fault zone, but you get a huge number of faulting segments above and below and within the slip zone, which tell you it's not a simple slip plane. Now, of course, of fault damage, it's been a lot of work starting 2005 with the paper by Benzion, which I show, by Andrews, which I show here. And probably the latest one is Xu et al. Here in 2015. So 10 years have passed, and we learned how to do color scales. But the message is always the same. As the rupture propagates, the width of the damage zone becomes wider and wider. Okay, and the tip of the rupture is here. So you have the extended damage. And these, of course, all use model of rheology for brittle material, inspired by Liakovsky et al., for example, but they don't provide any localized slip zone as we observe in natural fault zones. They are a diffuse model of the formation, even if it's brittle. This is something else that people have been looking at from the field perspective. They've been counting the number of fractures as you go away from the main fault zone and see that, okay, they decay very rapidly. And of course, this is very important for the permeability of the fault zone and probably for surface energy that's required to create those cracks, but they not necessarily use a big amount of energy. They don't necessarily dissipate a big amount of energy. Because in my vision, dissipation or the dominant energy sink is mechanical work, which is the product of stress and strain. So you need strain. It's not enough to just open a crack. You need to make it slide, or you need to deform it to get a decent amount of energy dissipated. And so you can write the mechanical work as the sum of an elastic contribution and an elastic of this part is recoverable. So we're going to forget about this and just talk about anelastic strain. And so even apparently ductile or diffuse strain is in fact accommodated along many tiny slip surfaces if we are in the brittle domain and not in the plastic domain, which is the case for most earthquake faults. And because plastic, viscous, or particulate flow is marginally triggered by earthquakes, except for the principal slip zone and high slip velocity, as Giulio was explaining earlier, and probably in deep earthquakes, as Alex was explaining earlier. You have plastic behavior, but not outside the principal slip zone most of the time. So the work of frictions, the work of mechanical dissipation is product of stress and strain. It can be shown that if slip is localized, it becomes disintegral with slip on the fault. And if you have a series of faults, it's the sum of the work on each single of these faults integrated in the same way. And you can build that into the energy budget again, and you can argue that this term here, which is the off-fault damage, can be replaced by a sum of frictional work on a series of faults that are surrounding the main fault strand. So if we measure this dissipation only in the lab experiments on one principal slipping zone, 5 minutes, okay, we're going to get only part of the picture because we'll miss the off-fault deformation. Now, let me take you rapidly to the field. This is not thrust earthquake. It's very different from what happened in mega quakes. So these are probably magnitude 6 events that I'm going to show you. But I'm arguing that this is a sort of analog natural experiments for what happens at the bigger scale in larger faults. So these are faults in poorly lithified sediments that show evidence of seismicity, very, very clear evidence of seismicity through these seismites, which is not the Hebrew version of marmite. It tastes very differently, believe me. And so they're very well defined because they are also correlated to some archaeological damage, which can be historically dated. And the composition can be quite similar to what you would find at the ocean trench, although these are lacustrine sediments. This is how they look, and you have a principal slip zone, and then you have second subsidiary slip zones, which are a few millimeters thick, and you can do a census of those and look at how much slip because of this very tiny stratification here. You can look at how much slip each of these accommodated, okay? This is on a scale of 1 meter. The whole fault zone is a few tens of meters. Of course, because of Brexit, now we have to use British pounds for a scale, and it's better if it has the Queen's head on it. This is a tiny subsidiary slip zone. This is the principal slip zone, and you can measure all these things, and then you can take some of this gouge, bring it to the lab, and measure the friction, okay? Now let me just do an artistic vision of what happens for a rupture that propagates on some more or less predicted existing fault. It concentrates stress in a lobe, and within this lobe, you can expect secondary fractures. And as rupture progresses, one of the fault wins. It gets weaker than the others, and the others basically become inactive and are left behind. And then slip is localized, and fracture progresses and continues to make this array slide. And as this concentration gets bigger, the rupture region affected is getting bigger, and you have more and more subsidiary cracks. Now, if you look at the frictional behavior, and we're interested in the area below this frictional curve, which is the dissipated energy, the main fault will go like this, and will stop somewhere here. And the small faults will slip less, so they will have a tinier amount of energy, and the smaller slip, of course. But there are many, many more small faults than the big one. So we're shearing this array of system. The effective slip is the sum of all the slips, but the effective stress, because of stress continuity, is more or less the same across the fault array. And then if we zoom this initial part of frictional behavior, although it's very tiny, but we sum it on a large number of small faultlets, we got a decent amount of fracture energy. So again, this is what we're summing here. So this is the distribution of the faults across the transect. So you get three principal slip zones that correspond to 3 main earthquakes. And this is the slip distribution on all the fault sizes. And besides some perturbation linked to the fact that you have several fault zones, this looks most likely like a power law, not very surprising. And if you factor in the deformation taken up by the subsidiary faults, you are able to fill the gaps in the slip of the main fault. So you get a much smoother distribution of slip, which looks like these things are necessary for the general slip of the fault. And then if you take now the experiment in the laboratory would give you this type of energy, which increases very fast at the beginning, and then the fracture energy saturates. But if you take all the subsidiary faults and the slip that they accumulated, and suppose that they all follow the same more or less friction law, and you add them together, you get this fracture energy here. Of course, the cumulative slip is much larger. It's about 3 times that of the principal fault zone, but the fracture energy is about more than 10 times as much. So this is very surprising, and in fact it's because those tiny faults are all in the initial part of the weakening where the stress is still pretty high. So even as the slip is tiny on these faults, the stress is high, and you have many of them, so they dissipate a lot of energy. And so they magnify the frictional work. Now, how much? 2 minutes? Also, just for the fun, if you posit that velocity hardening favors distributed slip and velocity weakening favors localized slip, you'd have the initial slip, which is slow and is velocity hardening, and then you'd have distributed slip. And you can show that if the total velocity of the fault array is the sum of the faults that you cross, and the total slip is the sum of the slip that you cross across the transect, then the average velocity on the subfaultlets would be the total velocity divided by the number of faults. However, the average stress would be the same for all the faults, again, for stress continuity. Then if you plug in these values into a friction law, which has a velocity dependence, of course, the velocity will drop inversely proportional to n, and the total work will be the total slip times this friction value. So if you have frictional weakening, this is going to drop. If you have frictional hardening, this is going to increase, which means that if it slides slow, you're going to favor multiple folds. If it slides fast, you're going to favor single folds. And that is possible explanation from what happens in progressive localization and dissipation during the initial part of rupture. Okay, that's all. So conclusion on natural fault zone, you have many subsidiary faults that are expected to be active in the initial part of the slip where slip is not yet localized on a single strand. Here I showed an example of a very superficial and very mature fault in unconsolidated solid, which I use as an analog a little bit for what happens in faults. Secondary slip zones accumulate small slip individually, but there are many more, and they slide under high stress in the initial part of the weakening curve. So they are able to build up an effective frictional dissipation, which in this case of the Dead Sea Masada fault was about 10 times as much as what you would measure on a single fault in the laboratory. So knowledge of typical coseismic slip distribution on a fault array may allow to recalibrate laboratory experiments in terms of fracture energy to feed into our modeling. And open question, probably this field evidence lacks of generality. Do we have similar outcrops on major faults if we know that they have been seismic or not? Thank you very much.
Thanks a lot.